Hello, and welcome to this Year 12 physics taster lesson. So, if we were in school and things were normal, you would probably be doing a taster lesson on. Basically, we'd be trying to do an experiment on how to measure g. G is the acceleration due to gravity on this planet. It's different on every planet, so we can only do this one. And it's a different experiment because we know the answer. And so it would be about trying to recreate conditions to get our answer as close to the real answer and doing it as precisely as possible. So, if you do it once and you get a lucky dip, that's not necessarily the same as being able to do it repeatedly. Let's just get you thinking. Actually, I've written here at the start, recall any equations that have acceleration in them. That's a good place to start. But also, can you remember what the words accurate and precise mean? And so that'll help us when we're going forward. So why don't you just start yourself off, pause the video, and try and remember any equations that have acceleration in them, and what do the words precise and accurate mean? Pause and then unpause once you've had that go. Okay, so the word accurate, it means, it kind of means on target, I suppose. If we are accurate with our results, we will get results that match the actual accepted value for gravity. So, for example, 9.81 is a good example of what it is. So, if our value is 9.81, that is very good. Precise, well, precise comes from doing the experiment multiple times. And every time we do it, if our results are grouped closely together, that means we're doing the experiment precisely, as in, so how close or how much spread is there in your results? Basically, if we get 9.81 once, which is brilliant, but if the next time we get 27, that's not brilliant. That makes our results very imprecise. So precise is how close are your results together, and accurate is how close are they to the accepted value. Now, ideally, you want both. You want accuracy and precision. Precision is quite good, but if you're not very accurate, if every time you get 20 as your value for acceleration due to gravity, and you get it like 10 times in a row, well, you're precise. That means you're doing the experiment the same way each time, and the results you're getting are sort of reliable or repeatable, but they're not very useful in the scheme of things. So what you want is a combination of accurate and precise. As a consequence, though, by being more precise, you may lose accuracy, or by being accurate, you may lose precision. So these two things we have to balance out. Let's think of some equations that have acceleration in, though. The simplest one, F equals ma force, is mass times acceleration. Another one, we've got acceleration is change in velocity over time. That's another good one. We could have this one, v squared equals u squared plus 2 times acceleration times displacement. V squared equals u squared plus 2as. What else do we need? You could have s equals ut plus a half at squared. Now, if I taught you GCSE, I didn't teach you this equation because you didn't need to know it. But it's very important for what we're doing today. We've got 4 equations. It's a good place to start. So let's move on to the next step. So at different points on Earth, objects fall with an acceleration between 9.764 and 9.834. This is depending on altitude and latitude. Actually, the Earth, although most people think of it as a sphere, it's kind of slightly more compressed in the middle. So around the equator, it's a bit denser. If you're near a mountain, large masses like a mountain will slightly affect gravity. So all these things mean gravity is not like one particular fixed number. There is a range. But that, if you look at those two numbers, they are very close together. The common version, the common standardly used value is 9.81. At GCSE, you would have been using the value of 10. But at A level, we're going to be slightly more specific. and we'll use a value of 9.81. So that's what it is. You know the value of gravity of 9.81. Can we actually calculate it? Can we do it accurately, and can we do it precisely? And some of the things now, this is an experiment where you can do at home. You'll need the most basic equipment. So let's have a go. Okay, so the first experiment is nice and simple. You just drop the ball and you time how long it takes to fall. And here's the equation we have. S equals ut plus half at squared. Let's just review. S is displacement. U is initial velocity. T is time. Half is a number, it's constant. A is the acceleration. Oops. And T is time again. And squared is mathematical operator. So, first of all, we need to rearrange this equation. I don't know how comfortable you are about rearranging equations. There's quite a lot of things in here. I'm going to give you a little simplifier for this equation. So this experiment starts, it's a picture of somebody doing it on me. This equation starts with somebody dropping a ball from rest, and then timing the ball as it falls. Now, it's quite tricky to do this precisely, but you can do this by just using a stopwatch. Maybe you can do it with a video camera, recording the ball, doing that sort of time. So there are different ways to be able to do this, but the important thing is we drop the ball from rest. So that means the initial velocity equals 0. If the initial velocity equals 0, then the initial velocity multiplied by the time also equals 0. So for this situation, the equation simplifies a lot. It actually becomes S equals a half at squared. S is a half at squared. Simpler, much simpler to rearrange. Do you think you can rearrange? If you can, pause and do it. Someone's at the door. I have to go get it. Okay, so let's try rearranging this equation. So, first thing I would do is I would move the half from this side to this side, so that you are multiplying by a half there, which are the same as dividing by a half there. Those of you who are comfortable with maths should hopefully realize that dividing by half is the same as multiplying by 2. So actually I can rewrite that as 2s. So 2s equals, a t squared. Well, the t is squared, but it's not t we want, so we can just leave the squared there. So we just bring that down, divide by t, 2s over t squared equals a. Excellent. So what we need to do is we need to record the distance, the displacement. So that's how far the ball is dropped, and the time it takes for the ball to drop. And this is where the precision comes in. How can you make that measurement precise? When you're making a measurement, say with a meter ruler or a tape measure, you're probably going to be able to measure it to, I don't know, a level of precision, a resolution of about maybe 1 millimeter, maybe 1 centimeter. So if you're measuring a 10 centimeter distance and your uncertainty is 1 centimeter, that's 10%. That's a huge amount of uncertainty. So if you measure a meter and you've got 1%, 1 centimeter, that means your uncertainty is 1%. In fact, the bigger or the larger the distance you measure, the smaller your uncertainty or unreliability becomes, so hopefully increasing your precision. So to make this better, you drop it from a long distance. The longer the distance, the better it can be. Time is very difficult to be precise with it. You've got reaction time and everything. Again, if it's falling a longer distance, it means it'll be a bigger time, so it'll be easier for you to measure. Maybe you could, if you've got, most of you will have a smartphone, and on that you'll be able to video it and record it in slow motion, and maybe that'll make it able to do precise measurements. So what you need to do is you need to record your distance in a table, and you need to record the time in a table. And then once you've done that a few times, you can put those values into the equation and get a value for A. Another method of doing it is using a pendulum. Pendulums are basically very simple to make. You need a piece of string. You could use anything from a shoelace, string, cotton. You need a little thing on the end, something like a center of mass, which can be like a ball, and something easier to tie on the end. It doesn't have to be circular, but just something that kind of give a bit of tension in the string. And it doesn't matter. Pendulums are things that I should have made one in advance, but I haven't. Pendulums are things that it doesn't matter how hard or you drop them. It doesn't matter from what height you drop them. There we go. Self-made pendulum, just a USB and a lanyard. It shouldn't matter how hard. If you release the pendulum from this high, or if you release the pendulum from that high, it doesn't matter where you release it from. The time it takes to do an oscillation, so we say here, that's one, another one, that time is the same. Pendulums, the length of time for a pendulum's oscillation completely independent of how high or how big the swing is. If you only have a small swing, the pendulum moves quite slowly. If you have a big swing, it moves quite quickly. It covers more distance. But the time for that swing is completely the same as the time for that swing or that swing. They're all completely the same. The only thing that changes is the length. So if I have the short pendulum compared to if I have a long pendulum, it's only the length of the pendulum string that affects the time period of the oscillation. So, okay, let's try and rearrange this equation. So we move the 2 pi across, so we have t over 2 pi equals square root L over G. Bring the square root, so if you square this side, then we have, keeping it tidy for now, t over 2 pi all squared equals L over G. The next stage is basically, we want G, but we don't want G on the bottom. We can basically swap the position of this G here and this t squared, t over 2 pi all squared, to give us the equation we want, which basically means L over t over 2 pi all squared equals G. Now with this experiment, the tricky thing is, how do we make it precise? The measurement of the length, obviously, the longer the ruler, the longer the pendulum, the bigger the time period. So again, having a long pendulum like this is going to be better than having a really short pendulum like that. So making a long pendulum, but obviously there's a sense of space. It's going to be levels of complexity. The other thing is, how do you measure that accurately? That's a very small time, just about a second. Okay, what could you do to improve the measurement of that time? Remember, a pendulum is the first way that, one of the first ways they made mechanical clocks was with a pendulum. Pendulums are good at keeping time. So the first swing and the second swing and the third swing should all be the same time. Obviously, there's going to be a bit of friction, so it will lose some time as it goes. So after 20 swings, it may have lost some of its time period, but the first and the second and the third and the fourth and the fifth and the sixth and the seventh and the eighth and the 10th swings should all be the same time. So how can you use that principle to get an accurate measurement for one time? There's a very simple answer to that, but I'm not going to tell you. So another time. What I'd like you to do is record the length and then record the time. Do this multiple times. Record different values for G. How many times do you do it? Obviously, the more times you do it, 4 or 5 times would be good. Plug those in. How accurate are you? How precise are you? So, what can you do to reduce uncertainty? And what can you do to improve accuracy? What can you do to make your results precise? And then have a go. How close do you get to G? How close do you get to 9.81? And how many times can you get it close to 9.81? What can you do to make sure that each time you do it, it gets better? If you do it once and your results are awful, how can you modify that? What do you do? Maybe we'll do this when we start the year in September, back in school, hopefully. And we'll see what you've learned from this process. Okay, thank you. Bye.